All right, let's start. Do you have any questions? Okay, so we'll be finishing exotic options today, and probably starting American option. All right, let's see how far we can go. So we kind of touched on most of the things already. What's left to do today is to derive the PDE, right, for loopback and Asian option. And then also derive the analytical formula, right, for loopback option. All right. So let's focus on the PDE first. For the PDEs, right, of the loopback and Asian options. So like I said before, right, actually, let's take a step back. The point of the PDE, right, in this option pricing business is kind of a special tool, special concept, right? It kind of make a connection, right, between a deterministic function, right? I mean, it's hard to say what form it is, right? But the point is, it's deterministic, all right? Right, with a stochastic object, right? Which is, of course, right, the price of the option, okay? And so normally, right, you would feel like, so I mean, there's kind of like easy candidates, right, for the X, for example. Normally you would feel like, okay, so X, right, would be ST, for example, right, like the Black-Scholes call option. But as I kind of started last time, when it comes to more complex derivatives like exotic option or even like, let's say, American option, right, it's unclear, for example, how the relationship can be formed. Okay, in other words, the fact that there is such a function, right, there is such a deterministic object, and then something else, such that when you plug into this deterministic object, right, you capture, right, the price of the derivative at any time. That kind of property, right, the connection, right, the search, right, for suitable, right, process, let's say, let me call it just XT, all right, really is the stock, right, and YT, etc., right, and something else maybe, right, to plug in so that, right, somehow the equality holds, right, for any time, like this. This, right, exactly is the Markov property of the option itself. Okay. Now, this, right, is actually a little bit more subtle, all right, than how it seems like, in terms of the presentation right here. Because, right, for example, let's say you have the loopback option, right, or the Asian option doesn't matter. Let's take the Asian option, or let's take the Asian call. So VT, right, is the average price minus K plus. All right, like this. And then the pricing formula, risk neutral pricing formula says that this is this. Condition on FT, okay? And that's all it tells you, right? That's all it tells you. And notice that, again, hopefully from Math Finance 1, you remember that this notation, right, this filtration notation or the sigma algebra notation means the entire history, right? The history of the path from 0 to t. In other words, the pricing formula says that you have legal access, right, to the entire history of the path from 0 to t, right? By the path here, we mean the stock price path, but also the Brownian motion path, because there's a one-to-one correspondence between the two. If you know the stock, you know the Brownian motion. If you know the Brownian motion, you know the stock, right? On the other hand, right, as I explained last time, the path cannot be input into this object, okay? Because the path is a infinite dimensional object. Yes, I mean, you need infinitely many points to properly, right, capture the path from 0 to t. While here, right, if you look at this object, it allows you 3 spots, right? So R3, I mean, forget time, right? So actually it allows you two spots, right? Well, so the number of spots here actually also doesn't have to be like 2, you know, it could be 5, who knows, right? Maybe you have to include 5 objects in here to completely capture, right, V low t. But the point is, somehow it's a finitely many you know, dependency, right? That's actually what Markov property implies in general, that you only need finitely many objects here to somehow capture an infinite, okay, history of the past. So yes, there's some kind of dimensional reduction in here in some way, right? The path is an infinite object, but somehow you only need finitely many information to completely capture that. Now, of course, right, this in general cannot be done in the sense that if you just take any good old path, you definitely cannot, right, reduce it to just 2 dimension. The point though is here we're looking at a highly structured, right, product, or we look at a highly structured calculation where, right, intuitively speaking, the calculation somehow only centers around this object, okay, and nothing else. And that's what allows us to do this, okay? So in general, right, this belongs to this discussion right here, right? The Markov property of a stochastic process doesn't have to be option price, some other things. It's fascinating, and you know, we don't have time to go into this discussion in this class, but basically, you know, in terms of modeling, right? Like there are processes that look kind of complicated in terms of the dependence on the path, on the past history. Like somehow, right, when you look at this, it seems like this is overly complicated. You cannot imagine how, right, this right here can be reduced to dependence only on 2 objects. But so the point is, right, first of all, let me say this, right? The point is obviously, right, VT in this agent call, right, cannot only depend on ST. All right. In other words, if I only give you the stock price at time 0 t, there's no way you can figure out the option price, the agent call option price. Okay, there's no way that can happen. Well, why is that the case, right? It's kind of clear, right? Because the option payoff, right, depends on the integral, right, the entire integral, right, or the average price. So here's T, right? And let's say the stock moves like this. If I only give you S little t, meaning I only give you this point right here, right? Then of course, at time big T, right? You don't know if you only given this point, you cannot get the entire area under the curve, right? Like this, okay? Or for that matter, right? Given this point, you cannot know the entire area under the curve right here. On the other hand, right? The point of like the general Markov property is that you can increase the dimension of dependence, meaning that, okay, so one-dimensional dependence does not do it. But if you include one more object, all right, then somehow that will capture the entire dependence, right? So this right here can be reduced down to basically ST and something else, right? Like that. So that's the trade-off, okay? So that's the point. And so what is this object, right? What is this object? And as I alluded to last time, right? This object, of course, is something very natural. It is the integral, sorry, right? The area under the curve, right, of the stock up to time little t, right? So like this. So if you are given, right, the stock price at time little t, as well as the area under the curve, right, up to that point, then that's enough. That will be completely enough to capture the option price at that time. Okay. Now, so first of all, this fact is significant, like I said. But second, right, you should always ask why. Why is this true, right? How do you believe that this is true, right? Because, right, the reduction, like I said, may be not always true. You know, maybe someone claimed this and this seems true, but when you really investigate into it, you say that no, that cannot happen. That's not enough information for me to decide. You know, the stock price, the option price with only this much information. So the intuition, right, is, or like you can do the math, right? You can basically work out this complicated expression and see how dependence goes. But the intuition probably is more natural. It's like this. Try to check, right? If you're given this many information, like this and this, then the future, right, payoff can be completely determined. All right. So you check if this is enough information for you to tell what this guy is. Because if you can, then that means that from here, right, you can trace back the current option price. But if this is not enough for you to tell what the future stock price, the option payoff is, then there's no way, you know, that the current option price can be captured with this many information. So let me demonstrate this, right, with the simple vanilla call option. So probably by now, right, you are so used to this that you don't even think too much about it. That for the vanilla call, right, the value of the option, the call option, can be captured, right, by a function of t and s little t. All right. So it seems natural, I guess, but you should really question why is this true. Now again, right, the Black-Scholes formula already tell you, right? Black-Scholes formula already tell you that again, right? V, right? Vt is st NV plus minus k e to minus r t minus t NV minus. So, but just by staring at the formula, you can tell, right? By staring at the formula, you can tell. But that actually is a little bit begging the question, right? How do you perform this calculation to begin with? And sometimes, right, in the more complex option, you don't have the formula to tell you, right, what the dependence is. If you follow this intuition, okay, if you follow this intuition, then what does it say, right? The payoff, right, is st minus k plus, right? What are we given? We're given s little t, right? So the question is, if you're given s little t, can you tell the future payoff? Well, what does it take, right? What does it take? Well, what it means is this, right? Well, how is the future stock price dependent on the current stock price? Well, this is easy, right? Because that's just the Black-Scholes model. It will be s little t e to the r minus 1/2 sigma squared t minus t plus sigma, right? W tilde big T minus W tilde small t. All right. So what do I mean by, right? If given this guy right here, then this can be completely determined. Well, it's completely determined in the sense that, right, the information I need is noise, meaning, right, so these are future noise, which of course, right, is not my responsibility to know, right? So when I say completely determined, this language is a bit loose. I don't mean that I will know the future noise. No, I don't know that, right? But that future noise, right, is not my responsibility. In other words, it can be generated by, let's say, a Monte Carlo process, for example, right? You just generate a new Brownian motion, right, and obtain the future stock price. But all the kind of like the starting information, right, anything that needs to be generated, right, besides this future noise, are completely given in the information, right? So this is not my responsibility. All right. Notice that this is also completely independent of the current information. So basically, you start fresh, right? Given from this point, you start fresh. But if that's the case, right, then given this current stock price, you start fresh and you generate a future noise, then you can completely calculate the future payoff. Then that, right, will allow you to determine the current stock price. Yes. So in that sense, it is correct that the current Black-Scholes call option, right, is only a function of T and ST. Does that make sense? Okay. Maybe, right, another intuition is that if you are like really trading this option, right, if you are trading this option at this time, right, you would ask yourself, what do I need to tell how valuable this option is? And you can convince yourself that all you need to know is the current stock price, right? You don't need any past information. You only need the current stock price to gauge how the future stock price will be in terms of probability, right? And then that will give you an assessment of the current option value. So now, right, let's take a look at, for example, the Berry option, right? Up and out. Like I keep emphasizing, right? For up and out call, if you are given the stock price at time little t, it's not enough. It's not enough to know the future payoff, right? So in other words, VT, the value of the call option, is not exactly VTST in this case. Why? Because starting from here, right? Starting from ST, you can generate, actually, right? You can generate the whole future path. So from that point of view, you actually will be able to figure out if future, right, knockout potential can be evaluated. So in other words, from here, you will be able to completely determine if in the future you will be knocked out, meaning will you be above the barrier, or you will not be knocked out, so, and you survive. So everything from here in terms of future barrier behavior can be completely determined. The one thing you cannot determine is you has been knocked out in the past. All right. In other words, if you're here, right? If you're here, you don't know if the option has crossed the barrier sometime in the past or not. That's not part of the given information. Therefore, right, an up and out call technically is not a function of T and ST. All right. However, because of this information, or because of this analysis, right, VT is actually equal to T and S, VT and ST on the condition that it's not knocked out yet. So it's kind of simple, right? It's kind of simple. That if it's not knocked out yet, then because all you need is the current stock price to determine all the future behavior, including whether or not it will be knocked out. Therefore, right, if it's not knocked out yet, you're good. But this information also needs to be included into, right, the determination of the option bound. Okay. And for this reason, right, for example, if you look at something like up and in, right, let's say up and input, okay, then if you are at the current time t, right, and you're given st, it's hard to tell what option value it is. Why is that so? How is it that if I only given, so this is not true, right? Given only the current stock price, I cannot tell what option value it is at that time, right? If I'm only given the current stock price for the up and in, for example, right? For the up and out, right? The analysis is clear. I don't know if it has been knocked out yet. If it has not been knocked out, then yes, I will know it because all future paths I can generate it. How would the analysis be for up and in? Why is it that given only the current stock price, I cannot know what the current value of the option is?
Because you need a condition that it went up or across the barrier.
Right. So let's continue with that, right? There are two scenarios. If it's not knocked in yet, right, by time t, or it has been knocked in by time t. Now, notice, right, that if somehow these two conditions do not matter, in other words, somehow the analysis are the same for these two conditions, all right, then what I said here is wrong. Okay. In other words, if somehow this does not influence how the option turns out to be, then indeed, right, all you need is the current stock price. Does that make sense? But somehow, if this is different, that means what I say is correct. Okay. So how are these different? That if you are not knocked in yet, or if you has knocked in by time t, how are they different? Can you say something that would simply convince anyone that these are two different scenarios?
I think for the second one, it would you're certain that you will get a payoff, but for the first one, you need the indicator function still.
Very good. You're almost there, right? So can you say even a little bit clearer?
Yes. So for the first one, it would be little v TST, and then indicator function that the max is greater than the barrier.
No, I'm not going there, right? And actually, the indicator function doesn't work like that. What I'm trying to say is this, right? And this actually was in your homework solution. If it has knocked in, and by the way, right, when you try to communicate with people, and by people I mean people out there in the industry, try to be as simple as possible, right? Don't bring up formula when you can. If it has knocked in by time t, what can you say? Right, but actually for teammate, right, it's actually both of them can be represented like this. Actually, right? But what's the difference? If it has knocked in, then what can you say about the option? Then it's just a vanilla call. Agree? So here, VT will be V Black-Scholes. Sorry, little v. Right? But if it's not knocked in yet, then this definitely is true. Do you agree? If it's not knocked in yet, then the value of the option definitely going to be less than the corresponding call option at that time moment. Well, so here, right? So this is what Karim was trying to say, but what I was trying to bring out is not about the exact representation, but just about the different scenarios in these two cases to convince that, right, this relationship cannot simply be captured by a simple VTST. Does that make sense? So yes, there is. Oh, sorry. Vanilla put. You're right, Jingmei, because I was saying put, right? Yep, vanilla put. Yes. Right. But basically, what I mean is the barrier part, right, has been dismissed, right? Has disappeared. Okay. So if it has been knocked in, then it simply is vanilla put equal. But if it has not been knocked in, then the value is definitely less than the vanilla put. Right. So for that reason, these two scenarios produce something different, right? Therefore, now you can bring in the indicator function, right? Now, therefore, right, the value of the option cannot simply be dependent on just a function of T and ST, right? So this is where you say now you need some kind of indicator function, right? And I'm not going to elaborate on, what kind of that is, right? We talked about that in the homework solution. But I was trying to talk about how you argue that an indicator function is needed, right? Because I mean, it seems like you put the need for indicator function even before you argue why there's a need, right? For example, like I said here, right? There is a need for indicator function only because, it's a difference between a zero value or non-zero value, right? But that's kind of simple, right? Here, it seems like, the dependence is not that strong, right? Or it's not that much dramatically different. Here is very dramatically different, right? If it has not been knocked in, the value will not be the Black-Scholes value, but is it going to be 0?
No.
No, right? It's some other function, right? It still has a positive value. Yes. So in that sense, the knocked in, right, is I don't know, it seems a little bit more interesting than knocked out, right? The knocked out is either positive value or 0, right? But the knocked in is very different, right? So therefore, right, but anyway, the point is though, right, that a simple VTST cannot capture the option value. Does that make sense? All right. So now let's take a look at our Asian option. For the Asian option, right, then what does it take? I claim that, right? So let's take a look at, let's say, Asian call. I claim that if you are given, right, the area under the curve, right, then you can determine VT. All right. Well, or let's say determine V little t, right? Maybe that's more precise. So first of all, let's ask several questions. Why not? Given this. You understand? So because, right, the option depends on the average value, the average price process of the stock. So when I say this, am I being correct, or should I say this? So that's the first question. Should I say this, or am I okay saying this? Notice, right, maybe I should give some other name, but whatever, like prime or something. Which one do I need? Or both okay? Both not okay?
Would it matter? Okay.
Why would not matter?
Because given YT, you can still find YT prime, and given YT prime, you can still find YT.
That's exactly correct, right? Because T is part of given information. So it doesn't really matter what you're given. In fact, right, YT is much easier to work with as a differential operation. So yes, that's correct, right? So trivial thing, right? But hopefully you pay attention. They're the same in terms of, given one, you can figure out the other. But this is much simpler to work with, right? Because we'll differentiate at some point, and notice the change in T here will be pretty annoying, right? So that's the first question, right? So basically the same, right? Second, why not YT alone? Okay. In other words, is it correct that for this Asian option, because right, it seems like it only depends on the average price process, right? So notice, right, saying less is not enough, but saying more is also not good either, right? You understand what I mean? So what do I really need ST? Maybe I don't. Right? Because maybe this is all I need, right? Intuitively, that makes sense because the value only depends on that average price process. So what do you say to this?
I would say because there's like theoretically infinitely many paths that can give you the same area or YT, but you kind of need ST to narrow it down.
That's exactly the right answer. That's very good. Exactly. Right. Because this area here, right, is just a number, right? So exactly like Kareem was saying, that so suppose you're given this path, right? It attains this area. Notice that a path that, okay, this is not really right a possible path, but suppose you just go horizontal and you end up here, right? So this is one option. I mean, one possibility. This is another possibility. Both of these possibilities will have the same area. Right? But obviously, starting from each of the point, you will have very different future. Yes? So obviously, well, of course, right? Now, why would different future path be problematic? Again, I think it's clear, but let's just spell it out. Different future paths is problematic because different future paths will give different future area under the curve, right? Which will completely change the payout. Is that okay? So therefore, right, YT alone is not enough. Is that okay? So now, right, maybe we still need the positive answer. Why are these enough? Are we sure it's enough? Because right, this shows that YT alone is not enough. But are we sure that just throwing in the current stock price will nail it? Because right, notice that throwing the current stock price doesn't nail the past path either. Agree? Because right, like what Kareem was saying, but we can just modify it, that given the current stock price and the area in the curve, right, like this, does it uniquely determine the past path, the past history? If I give you the current stock price and the current area in the curve, does that uniquely determine the past history, the past path? No, right? Again, there would still be many paths that would have the same area and end up at the same point. All right. So these two do not uniquely determine the past history. And that's exactly the point, right? Like I said here, that because right, if your goal is to reproduce the past history, then you obviously you cannot reduce it down to only 2 points, right? That's not the point. The point is to capture the future. You only need that much. You don't need the whole past history. That's the point, right? The point is not to say that the history is equivalent to only these 2 points. That's not the point. The point is somehow the future do not need that much information. You can do much less. Okay. So why would these two, we can just, it's enough for us to capture the future. Well, because, right, the future more or less only depends on this guy, right? This guy is the only thing that really matters about the future. The rest are just, constants, right? Now, this will be the integral like this, right? So this exactly is captured by the area under the curve, right? So it's like, the saying, right? The entire area under the curve can be captured by, right, two areas, this area right here and this area right here, right? Now, this area right here is completely known by the given information. This area right here, though, right, is allowed to be random because that's a future information. But to generate this future random scenario, what do I need? Well, I only need the starting point, right? That's all I need. I only need a starting point, and I can generate the future random behavior, right, of the path. Or if you want, right, in this symbolic writing, what you need is st e to the u minus t, r minus 1/2 sigma squared u minus t plus sigma w tilde u minus w tilde t, right? If you really want to write out. But basically, this is just saying that the future, right, value of the stock at time u can be completely generated by the current stock price with the future randomness of the noise. So this shows why these are enough. Does that make sense? All right, so that's right. That this is why, right? This explains why for the agent option, right? VT is VT STYT. Now I will skip, right, the part with the look back, all right, because it's exactly the same kind of analysis. I mean, similar, not same, right? And now I'll leave it for you guys to think about it. Of course, right? What is YT now? YT will be a running max, right? But try to figure out, right? Because the analysis is not quite the same in this way, that we break, right, the future integral, the entire integral, into the current integral plus the future, right? How do we break the max on the entire path? Using current information plus future. How
Are
do
you asking?
I'm sorry?
Are you asking?
What am I asking? Yes. What I'm asking is this, right? So the analysis, right, that allows us to conclude that for Asian option, it only depends on stock price and the current average value, the current integral, is because the future integral can be broken down into the current integral plus a part of the future integral that can be generated by the current value of the stock price. Yes. Now, I'm saying that with the look back option is a similar analysis, but clearly, right, the same operation does not apply. Yes, there's no integral here. So even though I say it's similar, it may not be, right? Because if there's no way for you to combine a future max with, let's say, the current max plus some part of the future. Yes, that's correct, right? That's exactly it. right? So the combination is a max of the YT and the future max. That's correct. And this part can be generated from ST, right? That's exactly it, right? The reason why I asked this, right, is because who knows, right? There may be some other object such that there's no combination of the path, right? Of the entire path by current and future value. Who knows, right? Maybe there's no combination. If there's no combination, then the discussion we've been doing so far doesn't work. Does that make sense? So, right. So even though it's similar analysis, you still want to kind of check that this kind of thing works. All right. Okay. So now that we have established that, right? Then how do we establish the PD? So for the PD, right, we rely on the martingale principle, except that there's something that we need to talk about, something further, right? That basically, E minus RT VT, right, is a martingale. So basically, whatever part that is dt, right, set equal to 0, right? So all well and good, except, right, let's take a look at what's going on. For the Asian option, right, we claim that, or we show, right, that this is the case, right? So therefore, E minus RT V T S T Y T is a martingale. Therefore, right, we can apply Ito's formula, right? And pay attention. When you apply Ito's formula, right, what do you have? You have minus RV, right, plus V sub t plus V sub x, right? RS. These are traditional part because of this right here. Okay. All of this, right? Let me do dot 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 dt, right? And then what do you have? You have, so there's an E to minus RT outside, right? You have E to minus RT, right? V sub x, sorry, V sub xx, right? Oh, you know what? I missed one thing, right? I missed 1/2 V sub xx, right? Sigma square s square. Still, there's something else. This is the dt part, and this is minus RT, right? V sub x sigma, right? S dwt. All right. So this is the martingale part, which we don't really have to care about, but let's just write that. So the point though, right, is so basically all of these that I wrote down come from these components, right? Like that. But now, right, for the Asian option, we have an extra dependence on the YT. So the Ito formula, right, is no longer as simple as this, right? So the Ito's formula need one extra part, which is the dot 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 part I was reserving, right? What is this dot 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 part? The dot 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 part, right, is what? Coming from V sub y, right? dyt. Agree? But it's not just dyt, right? Because we really want dt. So how is dyt compared to dt? remember that yt is the integral su du. So dyt is st dt. Okay. So we got okay so far. And notice, right, that here exactly is where I use the definition yt like this. Now, if I do the definition of yt as 1 over t dt, or 1 over t like this, then dyt, right, will be a mess, right? The PD is still right, but your definition of y will change, all right? So notice that the PD is written like this because I define the yt like this. All right. So the PD for the Asian option is minus RV, right, plus V sub t plus V sub x, or let me write x, right, because now we are in the deterministic notation, where x now is the standing value for s little t, right? But this, right, this is not just the PD, right? It's not just this equation. We need the domain for the variables, for example. So what are the remainder variables? T, right, is from 0 to little big t. What about the domain for the x variable? What about the domain for the x variable?
Is 0 to infinity.
Yes, right. X stands for the stock, and it's just positive. Now notice, right, that again, it's not just an empty question, because sometimes, right, the domain of the stock is not just bigger than or equal to 0, right? In the barrier option, right, it could be less than L or bigger than L, right? Who knows? What about the domain for Y?
It would also be just greater than 0.
Yeah, right, because it's the integral of the stock, and you know that there doesn't seem to be any upper bound, right, for the Y. So sure, that's all we can say. All right. What else? Is this all? What else? Again, right? Put yourself in the mode that you have to solve this numerically. What do you need to solve this equation numerically? Forget the numerical algorithm yet, right? Just what information do you need to solve this equation numerically? So you're in a 3D domain, right? There's the X domain. So usually, I guess in this way they would do this, right? X, Y like this, right? So what you're claiming, right, is you're looking at this, right? And this is a slice, right? At some t, right? At some t for the value, right, of the PD. So you try to solve this at a time, right? At any time in this domain. What else do you need to solve this PD?
The boundary conditions.
All right, very good, because you definitely need somewhere to start, right, to solve this PD. So tell me, what are the boundary conditions that you can say? So where are the boundaries in this PD?
at t equals 0 and letting x and y move freely.
So t equal to 0 is really not the right boundary to put the boundary condition. Why? Because that's what we're trying to find out, isn't it? Right? If you know the value at t equal to 0, and you're not solving for the p to be. I mean, financially, right? You don't really need anything. So yes, t equal to t, right? And what is this at t equal to t? Let's say it's Asian call. If it's Asian call, like what we've been doing, then what's the boundary condition at big T? This will be yes.
In this case, will we need to include the 1 over t?
Yes, Kareem, you are perfectly right. That's a good call. That was my error. Yes, because we define y as the integral. Yes. What else? What are all the boundaries? Is this enough? So this only allows you to trace back from big T back, right? But in this domain, you don't have anywhere to trace back yet, right? If you work from terminal time back, but what about the spatial domain? What's the boundary for x?
I think the boundary is at x equals 0.
Right. Go ahead.
I'm not sure if the value, if little v would equal 0 at the boundary.
All right. So let's take a look. So we're looking at t0, right? Y. Yes. So that's what we're looking at. And notice, right, these are not trivial questions. The reason is you definitely need this to solve the PD, all right? Because you need this part to start propagating information inside. On the other hand, right, how do you fill this in? What does this mean? So the stock at time little t is 0. It has had some integral so far. Well, what is the option payout? What's the option price at this point? It's a little bit weird, right? It's a little bit bizarre because stock price can never be 0, but well. So suppose ST equal to 0, right? VT is 1 over T integral SU du, right? Minus K plus like this. What can we say about VT if ST equal to 0? I mean, actually, we want to say V little t, right? No, Jingmei, not 0. Not 0. Because we have Y. Right. So for one thing, right, it's kind of like this. So the picture is something like this, right? You are here. So the point though, right, is once the stock dips down to 0, which is not going to happen in reality, but hypothetically, then it's going to stay flat. Yes. Yeah. So no, hold on. I think it's one of the big T. So it's going to stay flat, right? So therefore, this entire guy will be Agree? But that's the future payoff, right? That's a future payoff. So the current payoff will be, and there's nothing random about it, right? Because the Y is already determined. The stock is no longer, there's nothing random about this. So the current stock price will be, the current option price will be. Okay, so far. Yeah, because of the model. Right? But I guess it also makes sense financially, right? If the stock price goes to zero, what does that mean about a company? Goes bankrupt or something, right? I mean, it's worthless. So it's out of business. It doesn't, right? It doesn't stay any, it doesn't move any further. Does that make sense? All right. So what else? That's the X boundary condition, right? So which is this part. What else do we need? How about the other one? So this one is a little bit bizarre, right? I mean, y equal to 0. So you do VTX0. Now, it's bizarre in this way, in many ways. If y equal to 0, right? Based on the relationship between x and y, what must x be? Yeah, x must be 0, right? So if so first of all, right, based on the maybe, right, physically, if y equals to 0, it should imply that x equals 0. But let's just maybe skip that for a moment. Maybe let's just entertain an idea that somehow, let's say that, say the integral so far is 0 for whatever weird reason. And let's say that maybe that this company is just picked up at that point, for example, right? Let's just say that somehow magically it has a flat area and then it just jump up, whatever reason, right? But yeah, so anyway, let's just entertain this for a moment. So what I'm trying to say is mathematically, let's just entertain this idea. Vt is 1 over t s u du minus k plus, right? Can we decide v little t based on this information? Well, let's see, right? What it says is that Vt now is the 1 over t, the integral from t to big T of x, right? E to the r minus 1/2 sigma square u minus t plus sigma w tilde u minus w tilde t minus k plus. Agree? Because, right, the area from 0 to t is 0. So you only have the area from little t to big T starting at x, right? However, right, to find v little t, then you need to take the expectation of this guy and we're back to square one. because exactly, right, that we don't have an analytical formula for some expression like this. Okay. So basically, right, it's problematic from this point of view, but also it's problematic from the calculation point of view, because actually, even if you want to pose it, there's no easy answer here. So what does that mean? Does that mean that we don't have a boundary condition for y? Seems like it, but right, from the point of view of the PDE, that's not possible. The reason is you need boundary conditions to propagate information in, right? So you have information at x equal to 0, but you don't have information on the y. So you only have information propagating this way. You need you need information to propagate in the y direction too. Okay. So even though, right, so this is I'm just trying to explain, this is a difficulty, but on the other hand, it's absolutely needed that you have a boundary condition to solve, right, the P, all right? So how do we circumvent this? We circumvent this by something a little bit bizarre, but it's not that strange once you think about it. Instead, you put the boundary condition at y equal to infinity. Okay. Now, so we'll look at what this really means later on, but let's just see what the value is, first of all. Now, for one thing, right, if this is the case, we will want to switch to agent put. All right. In other words, Vt equals to K minus this. We'll explain how to deal with agent call later, right? So basically, right, the discussion above so far actually works for call and put, right? You can just adapt it. For example, right, you just do K minus this plus, K minus this plus, all right? That doesn't change anything. But for this boundary condition, right, I need agent put. Why? Because with the agent put, what is Vt x infinity? What would Vt be if little y is infinity? Zero, right? So because V future t is 0, this will also be 0. So in other words, in this picture right here, if you are looking at the agent put, then you have a boundary condition at x equal to 0, like this, right, with the put version. Also, you have a boundary condition here that is 0. Okay, and then you propagate information in. Now, what do we mean, right, by boundary condition equals to at infinity? Well, I think it should not be too surprising to you, right? That in reality, what do? We set a very high number, right? I don't know, depends on what high is, but maybe 1,000, maybe 10,000, right? You pick a very high boundary and you say that at that value is 0 or approximately 0. And then you start solving. Okay. Any questions so far? Now, so what about the call option? What about agent call? So clearly, right, we cannot do this, because this will be infinite, right? And it's not that, so infinite here is okay, because you just replace it with a very large value as a boundary. Infinite here is not okay, because infinite here means that this is where the value that you start propagating back in, right? This is the value of the option that you start propagating back in. And if you put an arbitrary value here, right, it will mess around with, so, right? So infinite here definitely is not okay, right? Is it okay? So does that make sense or not? So you cannot use this as the value of the option to propagate back in, right? Because that just makes no sense. This is okay, because that just means that you just try to pick the y value to be very high. So what do you do here? So what you do here, right, is you try to do this. Now, if you try minus infinity, then, right, clearly this will be 0. But there's one other problem with this way that you try to do it. The problem is that the domain, right, that you set up for this PDE is only this much. There's no minus infinity down here, right? So what do? So what you do then is, modify YT to be like this. All right, where Y0 is some free parameter set by the option. So Y0 will put 0 in the agent. So in other words, this is a common trick in math, and it might seem a little bit unmotivated. But what you're doing is you try to generalize the process you're defining, right? It may not have a physical meaning, as long as in the particular case you're really concerned with, you can plug in a value and returning to the original condition. But mathematically, right, there's nothing wrong with defining something like this, and then define the payoff as V big T is the S. So now you define the payoff as this 1 over T, Y big T minus K plus. Well, Y big T is this. Okay, so now it depends on one extra free parameter. So notice that this doesn't change any analysis that we've been doing so far in terms of the PD. Nothing is changed because this is a constant. However, the gain you get out of this the gain you get is the domain of Y now minus infinity to infinity. All right, because this Y0 can take on any value. Therefore, right, the true value that this can take can be anything. So it's quite artificial, but the point is that you redefine like this so that you can extend the domain here to the entire half plane like this. And then you solve, right, the boundary condition at minus infinity, and then you just extract the value at y equal to 0 anyway. Sorry, not y equal to 0, but some particular positive value of y, right? So that's a trick. Okay. So this part is a little bit technical. What I want to, right, bring out to you is that the PDE, right, for exotic option can be quite complex. First of all, notice that we have an additional Greek, right, popping in. This guy does not show up, right? So there's no definition of a Greek like this, right, in the classical Greek. Yes, but on the other hand, right, when you deal with exotic option, you can expect that the traditional relationship of the Black-Scholes Greeks may or may not hold because of this. All right. Second, the boundary condition for exotic options become very, very important, and it can be sometimes highly unintuitive to find out. But it's super necessary to work with those boundary conditions. Otherwise, you cannot solve your PDE numerically. Any question on this? Okay, so now let's quickly talk about the loopback option PDE. So the loopback, right? Do whatever you want. Let's say loopback call or loopback floating, whatever, you know. Right. So like I said, right? If you try to stay with the natural condition for the call, then you cannot have any sensible boundary condition to use. All right. It just, this number is useless. So if you, the direction of the call, right, likes to put this guy to be minus infinity. All right. Notice, right, 0 won't do it, right? 0 won't do it because of this problem, right? 0 won't do it. So you need to really push it all the way down, right? You need to push the part of the like this, right? You need to put y to minus infinity to guarantee that this whole thing is 0. Okay. So, all right. And now, right, that exactly does not work with the natural domain, like you mentioned, right? However, we still want to use it because otherwise, right, we don't have a boundary condition to work with if we stay with the positive domain. Okay, because nothing would work from 0 up. Nothing would work. We don't know anything. So what's the solution to that? The solution to that is try to rewrite our problem in a way that allows for this to be a legal condition. In other words, the solution is somehow try to extend the domain to this. Okay. And how do we accomplish that? We accomplish that by redefining what we mean by the YT process. In other words, right, if I were to tell you that the Asian call, right, the Asian option, if I were to tell you that the Asian option is no longer a function of just this, but is really a function of this, where Y0 is something that I specify when I start the option. Would that be illegal? Would that not make sense financially? No, right? I mean, this is as perfect an option as anything else, except that people don't really talk about this in the market, right? They talk about this, but that's fine, right? Because I can convert from here to here by letting my Y0 be 0. That's correct. That's correct. That is correct, right? So I will tag this extra one along, yes, as a part of my solution. Agree? But notice, right? In the end, right? In the end, I only need Y0 equal to 0, if you want, to give back to the answer to the classical problem. Does that make sense? So basically, I will solve the problem here, right? I will solve the problem here in this domain. Then I will convert it back to the original problem to answer your question if you want. Is that okay? Does that make sense? So again, right, it's a highly, highly unnatural trick. Yeah, I agree, right? What I'm trying to say though is I hope to explain to you why it's necessary. And it's necessary from a computational point of view, right? That without that condition, we just cannot solve, right, the option. Okay. So, all right. So yeah. Anyway, so we run out of time. So maybe let me right. Well, so we still don't finish this yet. We will continue on Monday, right? And definitely we'll finish this. Okay. So have a good weekend, and I will see you on Monday.
Thank you, Professor.
Yep. Thanks.